So, what if you could take a data pipeline that just crawls along, taking, say, 40 minutes to run, and make it absolutely fly in just 15? Now, that's not just some tiny little tweak, that's a massive leap in efficiency. In this explainer, we're going to dive into a real-world case of Spark ETL optimization and show you exactly how it's done. I mean, the results really do speak for themselves. The old legacy script on the left, a full 40 minutes. The new optimized version on the right, a breezy 15 minutes. We're talking about slashing the runtime by over 60%. So how is that even possible? Well, let's find out. To really get why the fix works so well, first, we've got to understand what was broken. So let's start right at the beginning with that 40-minute bottleneck and really unpack the inefficient legacy process that was causing all the headaches. Now, if you just glance at the old workflow, it looked, well, perfectly logical. It had 4 pretty simple steps. You define your data frames, which are basically just Spark's fancy name for a table, using some pretty heavy SQL queries. Then you do a count. Then you union the data frames together, and finally, you write out the result. Seems straightforward, right? But there was a critical flaw lurking just under the surface. And here it is. This was the big efficiency leak. For every single one of those actions, the count, the union, and the final write, Spark was going all the way back to the start and rerunning those super expensive SQL joins from scratch. It was doing these same intense, heavy lifting 3 times over. So, why would Spark do something that seems so inefficient? That question leads us right to a really fundamental concept in how Spark actually operates. The reason it recomputes everything comes down to a core feature called lazy evaluation. You know, the best way to think about lazy evaluation is to imagine Spark as this incredibly smart, incredibly powerful assistant who has a terrible memory. It won't actually do any of the data transformations you ask for until you force its hand with what's called an action, like .count or .write. It does the work, gives you the answer, and then, woof, it immediately forgets everything it just calculated. And while that can be good for conserving resources, in our case, it was the root of our entire 40-minute problem. So if Spark is forgetful by nature, how do we give it a better memory? Well, this brings us to the hero of our story, a command that's like a secret weapon for Spark developers. Let's talk about the .persist game changer, the simple command that gives Spark a memory. So what does .persist actually do? It's kind of like handing our forgetful assistant a notepad. It's a command that says, hey Spark, once you finish that huge calculation, don't throw it away. Save the result right here in the cluster's memory. And just like that hard-earned result is stored and ready to be accessed instantly. No recomputation needed. So how does this one little command help us build a much smarter pipeline? Let's take a look at the optimized workflow in action to see how reusing data just slashes the runtime. Okay, look at the new flow. The critical change is right there in step 1. Define and persist. We create the data frame, and we immediately tell Spark to save it. So in step 2, when that first action is called, Spark does the heavy lifting, but it only does it once. Then for step 3 and 4, all the later actions, it's just instant reuse. It just pulls that result directly from memory. The really crucial takeaway here is this. The computation happens once, and the results get reused multiple times. That is the entire secret behind turning a 40-minute job into a 15-minute one. It really is that simple and that powerful. But our story isn't quite over. I mean, giving Spark a memory is great, but a good data engineer always cleans up after themselves. And this brings us to a super important pro tip, using .unpersist to keep your cluster tidy and efficient for everybody else. So if persist is like telling our assistant to write something down on a notepad, unpersist is us telling them, okay, we're done with that now, you can toss that note out. It manually clears the data from memory. And this is so critical because it frees up all those valuable cluster resources for the next task, or maybe for the next person using the cluster. All right, let's bring it all home and summarize this performance win with a direct side-by-side comparison of the old way versus the new way. This table lays it all out perfectly. For data handling, we went from recomputing over and over to computing just once. For persistence, we went from having none to actively using .persisting. Our memory strategy went from being passive to being active, using .unpersist. And all of that created a much, much smarter logic flow. The difference is just night and day. So just to be crystal clear, what were the actual logic changes?
First, we figured out which big, expensive data frames were being used multiple times, and we used .persist on them. Second, and just as important, we added .unpersist calls right after we were done with those data frames. These simple little additions are what delivered that massive performance win.
Which leaves us with one final important question for you to think about. Now that you understand how Spark's default lazy behavior can create these hidden bottlenecks, take a look at your own projects and ask yourself, where is lazy evaluation costing you time in your own data pipelines?